background in statistical solid-state physics, complex systems, HPC, and machine learning. And his group at HZDR is helping to better understand laser plasma interactions by solving inverse problems in measurement data to establish experimental bounds for parameter space exploration enabled by large-scale simulations and surrogate models.
Thank you. I'm also here substituting for Ankur Chakrabarty, who couldn't be here today. Actually, his work that I'm presenting here. First of all, a bit of context. You already heard about this. We're working on laser plasma, or laser particle acceleration, and this is one example of a setup like this. So, in some ways, there's no laser here talking about lasers, right? Okay. So there's this thing which is labeled LPA, the small cone thing there, where you have this blow up of basically this simulation view of what is laser backfield acceleration. And basically you see this small green bunch in there, which is basically the accelerated electron bunch, which you maybe heard in the Science Slam yesterday, riding the charge wave there. And so the gas in this case is hit by a laser. Electrons are coming out and going into this beamline, and the point of this beamline is basically at the end there's an undulator, for example. This is a possible application of this as a secondary radiation source where you can use this to create a smaller free electron laser where you can inject high energy electron bunches at with less resources than like a kilometer long linear accelerator. And so our challenges here are basically to tune these things, because the APA itself is a highly nonlinear process. Then we have the laser, which is sometimes, and also the gas, which are themselves kind of complex systems, and not necessarily like produce the same output at every single shot. And so we want to characterize what is coming out of this whole of the whole acceleration process there. And one thing to do is basically doing this while we also look at this beam time, to basically be able to correlate, to see when we have certain lasing going on at the end, that we can also figure out what did we put into the lasing and what came out of the specific setting or the specific shot of the laser, which will vary from shot to shot actually. So there are multiple diagnostics on there. You can see these pictures which are coming out there, where you have these blurry kind of density maps. These are basically the beam imagers. So the electron bunch is going through a fluorescent screen, and you see this pattern there, which is basically like a 2D projection of the whole beam going through. Since when we have this beamline there, and basically when charged particles go through a magnetic field, they turn a corner depending on their speed. And basically, you can imagine when you go turn a corner there, and then you go through this imager, which is inside the thing labeled chicane, the red boxes. The beam has been turned, but not only in 3D space, it has been turned in its 6D phase space. So we have like 3D coordinates in space. We have 3 momentum coordinates. And so, in principle, by kind of letting the electron bunch run these curves, we could extract information about more of the 6-dimensional phase space than just only the shape that it has in space. And also what we want to know, like how is the momenta inside the electron bunch distributed. So, and we want to extract these specific, ideally the whole shape of the bunch, but in principle, what we are starting out with here, specifically in this approach, is basically getting some properties, like for example the overall distribution of energy in our bunch, distribution of momentum directions, like basically the one perpendicular to the beam direction, so the divergence, so how much are they flying apart. And how are we doing this? It's basically we want to also know how much do we know, how much can we actually learn from certain measurements. And so we use simulation-based inference for that, where in the end what we want to have, and which is untractable, is the posterior, where given we want to know the probability of certain parameters. These are the parameters describing the shape of our electron bunch, given an observation that we can see. For example, images from these imagers there, or some other spectra, energy spectra, or radiation spectra that we get at the end of this beamline. And this posterior gets approximated in this approach by having a simulator likelihood, which is basically the probability of obtaining a given observation, like this imager image, given the parameters of our electron bunch, multiplied by the probability of our parameters there, which is basically like a uniform in our range. As a simple example, for example, if we have like a harmonic oscillator, we can run the simulation of this harmonic oscillator for a given spring constant here, and if there's and then we have a real noisy observation of a harmonic oscillator with these blue points there, then there are multiple things that could basically fit this whole thing. And so basically now we try to estimate this probability of kind of, given this blue dot observation, what is the probability distribution of our spring constants there, assuming in this case the mass is known or would be a different parameter. The simulation-based inference pipeline works in a way that we have input modalities, for example, different imager images or a single one, or also other modalities later. We first have an embedding network because to basically extract features from these. As you can see, all of these images, they are quite, well, low fidelity in some cases, so basically there's a lot of black around them. And also, mostly we're interested in, for example, like shape features of the whole thing. You can also see that's not like a fly with lots of small, tiny details. So basically having an embedding kind of makes the next step easier, which is the neural density estimator. There are different approaches for that. What we are using there are normalizing flows. And there's also other approaches like mixed density networks, which network that basically predicts coefficients for a mixture of Gaussian. That's then given our probability distribution, while the normalizing flow is a neural network that's invertible and basically trying to reproduce a certain probability distribution that is described by data. And then, for example, we can get out these probability distributions for values of our certain parameters, like the divergence, for example, gets a certain value, or the energy spread would have a bimodal distribution in this example. So basically, there are two possible values it can have given the observation. The simulation part of this is handled by a code called Elegant, which is developed at Argonne National Lab, and this is basically a beamline simulation. The amortized prior, that's basically just training that neural density estimator using purely simulation data, uses 200,000 examples from these Elegant simulations, which are sampled from basically a box, a 10-dimensional box of these parameter intervals, in order to be able to make predictions on this interval. There's one challenge about this, basically identifying this box first. We talk to the people who are running the experiments, what do they think should be the regions where we are in, which is always not always completely certain, so there's some things, sometimes you might not find a solution actually in here, but then nothing we can do, we have to then iterate, go back and say, expand this box. Okay, so we have then looked at basically to quantify the expected information given how much of the input modalities we are giving in. And so, for example, what you can see here is if we use one imager, so that's one of these projection images there, then we get, for example, for all of these parameters, we get certain values of information extracted. So basically 0 would be if it had basically as much information as a model that doesn't know anything. That would give us like a flat uniform distribution over our whole parameter range. And there are some parameters which it can extract pretty well, and others where it's kind of still mostly guessing. So some of these basically that would be the baseline model, or that would also be close to what it sees when we have these like 0.3 things there. And then we have other parameters where we can actually extract more information where it's kind of more distinct. And then basically if you combine multiple modalities, because as you see each of these different images, when you combine multiple images, there are different projections, as I said, of this whole 6-dimensional structure. So we can get more of this information out by combining them. And so they're basically just concatenated, the embeddings are concatenated, put into a neural density estimator, and then we can extract much more information about the different parameters. Then another interesting thing is basically actually applying this to experimental data, which always looks like slightly different. In this case, we did this for like one of the imagers here. This imager is basically one that's available, it's imager 2 at the front of the beam. And we can basically see that there's two bars, there's the horizontal and vertical divergence, which are here basically where the variance is smaller. That's where the model basically tells us, okay, there we have some information, and the others basically are nothing. So, which is kind of in line with the intuition about this, because by design of the beamline, this thing should contain information about the divergences there. In simulation, we have very clean data and such, we can extract a bit more information at the edges there. And so there's ongoing work basically, and basically adding this whole refinement of the prior with a training loop to the whole thing, basically by generating these samples and then retraining the prior on simulations based on these things. So, and yeah, we basically showed this information extraction for now, and we are going on to doing this whole loop, where we are also working on extending the challenge, extending the code to be able to utilize our cluster for the simulation loop. Thank you for your attention.
Great, thank you. Do we have a question for Jeffrey? Yes.
Yes. Yep. Thank you for your presentations. I want to ask two questions. So one question is that if I got you correctly, the Argonne people, they are doing a simulations for you, and they already have certain range of parameters there.
No, the code is from there. We are running the simulations.
Yeah, sorry. So sorry, I mean like the code from the simulations, they already have several parameters there. But then like, to what I see from your neural net, I mean, the model, your machine learning setting, you get an input of an image. Like, how do you, what is
the simulation, basically, the parameters are not fixed in the simulation code. They basically choose this parameter range, right, which we want to put in. The parameter range basically just describes like a set of possible shapes that of the electron bunch that we put in, like a six-dimensional bunch shape. And so it's mostly like more like a Gaussian-inspired, pretty flat shape. And basically these parameters just characterize this shape. And so basically, and then based on that, for each simulation, given set of parameters, a bunch of particles is generated that basically just samples this distribution. And this bunch of particles is then input to the simulation code, which propagates it. And then basically where we have in this beamline, we have the imager. We just basically compute this projection of the electron bunch, of the particle bunch, at this point in space on the beamline, to then get the simulated imager image, basically. So that's the output of the simulation, actually. So that's a diagnostic that we add to the simulation.
Then what are you doing with the Bayesian, with that probability, the calibrations? And then what are you calibrating? What is the prior that you're using? And then
the inversion of that. So basically,
yes, the inversion, sorry.
The output of the simulation, or the diagnostic that we get from the simulation and from the experiment are these images. And then we want to know the probability distribution of parameters that could have produced this specific output. Because often there are there's in some cases multiple solutions, or in some cases there are basically all the solutions because certain images, a single imager doesn't contain all the information. So then we would basically get like this uniform distribution overall. And so we know that this specific set of inputs doesn't give us information. So which is getting a bit more, then here we can verify with the linear beamline when we have, for example, when we add radiation information that we get at the end of this beamline, those are nonlinear processes or monolinear processes, so we can't as easily verify. So at first we look here where we actually know what should be coming out to some extent.
Okay, thank you.
Okay. Then we move to the next question.
you showed quite nicely that using several of those images improves your performance by quite a bit. I was wondering how you do this on a technical side. Are you just basically concatenating the features from the individual images, or?
They actually, there's an embedding network that's applied to each separately, just a CNN, which actually also inside the pipeline trained from scratch. But then the embeddings are just concatenated and put at the condition to the normalizing floor, to the neural density estimator.
Okay, thanks.
And we have time for the last question.
You are using the images that are coming out of your simulation, and then, I mean, you already mentioned that the images are very information sparse, right? There's lots of background and only very little signal. And you're solving this problem with an embedding that is trained, I guess. Could you also use like a more transparent algorithm that actually extracts the parameters? I mean, because in principle from the simulation, you already have access to the actual bunch parameters that led to this image.
Yes.
And could you extract those parameters from the image and use those for training?
Yes, this was also done before this work. It has some advantages. Basically, when you use like an algorithm, it gets more stable with respect to images from experiment and simulation looking different. So a neural network gets into some trouble there sometimes. Algorithm is more stable, but the problem is the algorithm inputs for one bias. So basically you are looking out for certain features, so you put only these in. That's what you provide. Actually you lose information when you do this. And also in terms of like student time, it does take a lot of time to handcraft these features. That's basically going back to where we were using support vector machines to classify images. It's like handcrafting features. And to some extent, that's what we are trying to avoid, especially when we go to multiple modalities, because then for each of the modalities that you add, in this case, it's each imager shows different features that are relevant. So you couldn't use the same processing for all of these images. And then when we add radiation spectra and we add maybe electron energy distributions that we can get directly from the bunch at the end of the beamline, then it gets complicated. For each of them, you have to basically do the study again to see which are the features that you want to extract from the whole thing.
Okay, thanks.
Thank you. With this, we have